Okay, we're continuing with Chapter 10 in the statistics textbook. In this video, we're going to go through the third section, which is on the regression method for individuals. So the regression method for individuals, what are they talking about here? Well, don't worry, we're not going into some brand new separate analysis for the regression method, okay? But what they're talking about in regards to individuals is, so if we come back to an example problem from section 1, okay, so let's take a look at this first example. It says in a certain class, midterm scores averaged out to 60 with a standard deviation of 15, as do scores on the final. The correlation between midterm scores and final scores is about 0.5. Estimate the average final score for students whose midterm scores were 75, 30, and 60. So all of the questions we've worked up to this point in the first two sections, when it came to using regression to estimate an output, the textbook would word the question from like a more average or group perspective. So estimate the average final score for just students in general whose midterm scores were this, right? If we come here, estimate the average income of those women who have finished high school but have not gone on to college. So 12 years of education. So the average income of those women in general, if a woman has only completed 12 years of education, so didn't go to college, what would you estimate the average income of those women to be? So with these questions, we were never honing in on like a specific individual. All right, now you might say, well, okay, but so what's the big deal? What's going to be the difference if we talk about a specific individual? Well, there's not going to be. You could absolutely take, if we come back to this first question, you could reword this question and say, if there was a specific student whose score on the midterm was 75, what would you guess their final score was? Or their score on the final? Well, just use the regression method. It's the same exact thing. There's no difference at all. Okay, so what are we talking about then in this section? Well, there is one way you can analyze individuals that you can't analyze if you're just talking about general groups. You can look at it from the perspective of a percentile. And so that's all they're wanting to talk about here. They're saying, okay, if you have a student or a person who ranked in the 90th percentile on the SAT, then where would you expect their percentile to be in relation to something else? And so I guess it's not really that easy to do that with groups, but at the same time, you could think about, for all the students that ranked in the 90th percentile on something, where would you expect them to rank on something else? So I mean, from that perspective, to be honest with you, I'm not really sure exactly what the textbook is talking about as far as where we're analyzing regression for individuals. This is still a really interesting section, and we'll learn a lot here. But as we read through this, you're going to see there's no new information as far as we do something different when it comes to regression if we're speaking about a specific data point, a specific individual. So, okay, for the men age 18 to 24 in Haynes 5, the relationship between height and weight can be summarized as follows. Average height 70 inches, standard deviation 3 inches, average weight 180 pounds, standard deviation 45 pounds, are about 0.4, positive 0.4. Suppose one of these men is picked at random and you have to guess his weight without being told anything about him. Okay, so it makes it sound like we're going to be doing something different because we're picking a single man at random, but we're not. Well, actually, okay, this is a slightly different question than what we've been asked so far. Okay, yeah, I'm sorry. So hold on. Let's look carefully at this question. Suppose one of these men is picked at random and you have to guess his weight without being told anything about him, so they don't tell us his height. We just have to guess his weight. Well, what would be the best guess? What's our best guess? Just the average weight, right? The overall average weight. So that would be the best guess there. Okay, but now next you're told the man's height, 73 inches, for example. So what would you guess is his weight? It's exactly what we've been doing. No difference. So, okay, how many standard deviations is this height away from the average height? It's 1 standard deviation away. So the positive 1. So we're going to go 1 standard deviation in the y direction, that's 45 pounds, but times 0.4. So 4/10, that's 2/5 times 45. So 18 pounds above average weight. So 180 plus 18, it's 198 pounds. Okay, so this man is tall and likely to be heavier than average. Your best guess for his weight is the average for all the 73-inch men in the study. This new average can be estimated by the regression method as 198 pounds. Yeah, so here's just a reminder of what the regression method is doing, really any curve fitting method for that matter. Your best guess for the weight of the 73-inch tall man, is the average height of all 73-inch tall men in the data set. That's the best guess. Can't get any better than that. Now, so the regression method estimates what this average is of the 73-inch tall men, their weights, 198 pounds. This is not necessarily the average weight of the 73-inch tall men, but the regression method is going to it runs smoothly through those averages. So the regression method is telling us that on the average, if you increase one standard deviation in height above the average height, then on the average, you're going to increase 18 pounds in weight on the average. The rule, if you have to predict one variable from another, use the new average. Yeah, but you're not going to be able to get the exact average unless you do like a spline fitting type method. But even with spline fitting methods, then if you bring in a data point that's like in the middle, so like you have to extrapolate between data points, then is that exact? But yeah, that's for any curve fitting method. Ideally, you always use the average at that x variable. In many cases, the regression method gives a sensible way of estimating the new average. Of course, if there's a nonlinear association between the variables, the regression method will not apply. So this section can be confusing. It makes it seem like they're talking about new stuff, but they're just restating everything we've learned so far. All right, example 1. A university has made a statistical analysis of the relationship between math SAT scores, ranging from 200 to 800, and first-year GPAs, ranging from 0 to 4.0, for students who complete the first year. So a university has made a statistical analysis of the relationship between math SAT scores coming out of high school and first-year GPAs of students that they admitted to their university. The results are shown here with the correlation of 0.4, positive 0.4. The scatter diagram is football shaped, which is important because otherwise we wouldn't take this very seriously, this being the linear correlation coefficient. A student is chosen at random and has an SAT of 650. Predict this individual's first-year GPA. So, again, this section can be kind of confusing. It's like, oh, so since we're choosing a specific student, we're going to do something different? No, you could just as well have asked, in general, for students that were admitted to the university and scored 650 on their SAT, what would you, in general, expect these students' first-year GPA to be? Same question. All right, so, I mean, yeah, you just do... how far is 650 from the average in terms of standard deviation? So 100 divided by 80. Okay, now get that same standard deviation in the y direction, the GPA direction, but then multiply by 0.6. And it's going to be that increase in GPA from the average. That's what they do, and they get 2.9 GPA. Okay, the logic... For all students with an SAT of around 650, the average first-year GPA is about 2.9 by the regression method. That is why we predict a first-year GPA of 2.9 for this individual. Yeah. Usually, investigators work out regression estimates from a study and then extrapolate. They use the estimates on new subjects. In many cases, this makes sense, provided the subjects in the survey are representative of the people about whom the inferences are going to be made. But you have to think about the issue each time. The mathematics of the regression method will not protect you. In example 1, the university only has experience with students it admits. There could be a problem in using the regression procedure on students who are quite different from that group. Admissions officers typically do extrapolate from admitted students to students who are denied admission. So yeah, if you think about this, you could get, they could have done this statistical study, got their curve fit, their regression line, and then just for all incoming students after that, just applied those students. They don't keep doing statistical studies. They just apply those new students that weren't a part of the original statistical study to the regression line for their estimates. Now, does that make sense that they would do that? Well, okay, my thoughts on it are that, yeah, I mean, if the initial statistical study was done with a large enough data set, maybe they did it for a 5-year period with a bunch of data points and kind of averaged it all out, and then got a regression line, and then then they just stopped doing the whole analysis, and for any incoming years that's how they did estimates for new students. Yeah, I think that seems all right, because they're saying here you have to make sure if you're going to extrapolate, and when they're saying extrapolate, they're saying that's saying apply like a statistical analysis or a regression curve fit, any kind of statistical analysis to subjects that aren't a part of the study itself. And they're saying when you do that, you have to make sure that the new subjects are representative of the people about whom the inferences are being made. And so, yeah, if you've got these new students coming in, they were admitted to your university. I mean, that's a pretty similar subjects, I would say. Again, if the statistical study was done with enough data points, then and you're applying it to a new student that was admitted to your same university, it's the same, like Harvard or something, the same, it's the same kind of person company that was admitted, right? So that seems pretty solid. But then it says here, admission officers typically do extrapolate from admitted students to students who are denied admission. Well, yeah, now you have a different. There's a lot of confounding variables there. You're applying the study to students that, when it came to the statistical study itself, these could be different personalities, different people. However, I'm not really sure what they're talking about. How do you extrapolate for students who are denied admission? Well, how are you going to estimate their GPA? They're not after the first year. They're not in your school. So maybe they're talking about, so they got denied admission, so they're going to another school, and they're going to estimate what their first year GPA is going to be at that school, which, yeah, now you're getting into different waters. You're going to be careful. Now, another use for the regression method is to predict percentile ranks, which I guess this would apply more to individuals, but I don't know. I mean, you could still talk about this in terms of a group, I think. So, all right, if your percentile rank on a test is 90%, okay, yeah, so reminder, what was percentiles? What was percentiles? Percentiles it was introduced as if you have a histogram that doesn't follow a normal distribution, then it makes it harder to apply analysis with the average and standard deviation because it's not like symmetrical. The average, I guess, but the standard deviation, it's more difficult. And so in those cases, a lot of times percentiles are used. But you can still apply percentiles with the normal distribution. So, and a percentile is just it's not a percent. It's in the units of the actual data set itself. So like SAT score or height in like inches, and it's like that if you're in the 90th percentile of an SAT score, then your score was better than 90% of everyone who took the test. That's the idea of a percentile. So they're saying that. So if your percentile rank on a test is 90%, you did very well. Only 10% of the class scored higher. The other 90% scored lower. A percentile rank of 25% not so well is not so good. 75% of the class scored higher. The other 25% scored lower. A percentile rank of 25% is not so good. 75% of the class scored higher. The other 25% scored lower. Okay. So now, example 2, this continues example 1 about the SAT scores and first-year GPAs. Suppose the percentile rank of one student on the SAT is 90% among the first-year students. Predict his percentile rank on first-year GPA. The scatter diagram is football-shaped. In particular, the SAT scores and GPAs follow the normal curve. Okay, so it's football-shaped, meaning we can be more confident about applying the linear correlation coefficient, but we also know that we follow the normal curve. And so we're going to use that to the fact that we're following the normal curve. Now we can tie this percentile to a z-score. And so let me go ahead and, so here from chapter 5, here's the formula for the normal curve. So you've got 100 divided by square root of 2 pi e to the okay, so there's the formula, store as e. Okay. Okay, yeah, so we can still do regression estimates here because these percentiles, in particular when they're applied to a normal distribution, we can tie to z-scores. And the z-score is really what the regression is all about, right? Because we're doing, you've got a certain number of standard deviations in the x direction. That's a z-score. And you time that to r times a certain number of standard deviations in the y direction. That's z-scores. So, all right, if we've got this student was the 90th percentile rank on the SAT, so how many standard deviations above average was this student? Let's start with that because we're trying to estimate his first year GPA. So with regression. So, all right, we've got, let's see. So integrate from minus infinity to z, the normal curve equation with respect to x. Okay, so we want to do, solve E is equal to 90 for z. Okay, wait, no, I need to solve this is equal to 90 for z. There we go. So 1.28. Okay, and so they used the table, got 1.3, but this is more accurate and easier. You don't have to always look up a table. You just put this in your calculator. So, okay. So this student was 1.28 standard deviations above average in terms of the SAT score coming out of high school. So, okay, if the correlation coefficient between the SAT scores and the first year GPA was, what was it? About 0.4. So what would we estimate the average, or what would we estimate this student's GPA to be? Well, okay, so it's this 1.28 standard deviations in the y direction, right? But times 0.4. So this many standard deviations above average. Okay, well, they're asking us about what would we expect his rank to be as far as his percentile rank to be as far as the first year GPA. Okay, and so he's going to be about 0.5 standard deviations above average in terms of the first year GPA. 0.5 standard deviations. That's the z-score. So what we want to do is translate this to a percentile. So you've got minus infinity to 0.512, and that's the area under the curve. So about 69.6%, about 70%. That's the percentile. Okay, so, and that's what they got, 69%. And so, yeah, it's interesting, we didn't have to know any information about the actual averages or the standard deviations. We could just work straight in percentiles. And that's what they said here. In solving this problem, the averages and standard deviations of the two variables were never used. all that mattered was R. And because we were working in just with percentiles, all you need is standard units. But the fact that it followed a normal curve. But then it's not like you couldn't use the normal curve. You'd have to. You could still use percentiles if you had the equation for the curve, the curve distribution that the data did follow. And just apply those same principles. That area under the curve is the percent, right, with a histogram. Basically, this is because the whole problem was worked in standard units. The percentile ranks give you the standard units. The student in example 2 was compared with his class in 2 different competitions, the SAT and the first year exams. He did very well on the SAT, scoring at the 90th percentile, but the regression estimate only puts him at the 69th percentile on the first year exams. Still above average, but not as much. On the other hand, for poor students, say at the 10th percentile of the SAT, the regression method predicts an improvement. It will put them at the 31st percentile on the first year tests. This is below average, but closer. Yeah, so for this particular study, it was the case that if you were in a high percentile, as far as the math SAT, then on average, the regression method is showing that on average, you're going to be in a little bit of a lower percentile in respect to the final first year GPA. But if you had a lower score on the math SAT or a lower percentile rank, lower rank, then the regression is saying that on average, your percentile is going to be a bit higher in regards to first year GPA. Now, but this is a little bit tricky when it comes to applying percentiles, like looking at a regression from the perspective of percentiles, because, okay, so let's keep reading and we'll come back to this. To go at this more carefully, take all the people at the 90th percentile on the SAT, good students. Some of them will move up on the first year test, some will move down, but on the average, however, the group moves down. For comparison, take all the people at the 10th percentile of the SAT, poor students. Again, some will do better on the first year test, others worse, but on the average, the group moves up. Right? On the average. It's not like every single student that did really well in the ACT, high percentile, is going to be in a lower percentile in regards to the final, but on the average, that's the case. Initially, many people would predict a first year rank equal to the SAT rank. This is not a good strategy. To see why, imagine that you had to predict a student's rank in a mathematics class. In the absence of other information, the safest guess is to put her at the median. However, if you knew that this student was very good in physics, you would probably put her well above the median in mathematics. After all, there is a strong correlation between physics and mathematics. On the other hand, if all you knew was her rank in a pottery class, that would not help very much in guessing the mathematics rank. The median looks good. There's not much correlation between pottery and mathematics. I mean, yeah, you can't just... They're saying that, you know, like your gut instinct might tell you that if you, without any other information, if someone does well on their SAT, was this math SAT or just SAT in general? Okay, yeah, just math SAT. Okay, well, maybe that would suggest that student's gonna be a good student and have a good first year GPA at a certain university. But I mean, maybe, but maybe not. You have to check what the data says, and the data shows here that that's not necessarily the case. Okay, now I realize you're probably scratching your head a good bit at this point. And so I'm going to address this confusion, but let's first go ahead and read this last paragraph. So it says, now back to the problem of predicting first year rank from SAT rank. If the two sets of scores are perfectly correlated, first year rank will be equal to SAT rank. at the other extreme, if the correlation is 0, SAT rank does not help at all in predicting first-year rank. The correlation is somewhere between the two extremes. So we have to predict a rank on the first-year test somewhere between the SAT rank and the median. The regression method tells us where. Okay, so why you're probably scratching your head a good bit is because, in particular with these last 4 paragraphs, it seems like they're strictly talking about the correlation coefficient like it's some pure parameter to indicate the slope of the regression line. So, for example, we're looking at the SAT scores and then versus the GPAs. Okay, well, all right, if we have a shallower regression line, then that's like, okay, well, you've got, higher SAT scores relative to the average, let's say, corresponds to not so high of an increase in GPA. And that's what R is telling us, right? So if you go a certain amount in the horizontal direction on the scatter plot, then the amount you go up in the up or down in the vertical direction is R times sigma Y. If R is lower in magnitude, it's less of a vertical movement. And so it's like, okay, they say here, initially, many people would predict a first-year rank equal to the SAT rank. This is not a good strategy. And why not? Because you have to look at the data. The data in this case shows R is equal to 0.4. All right, that's like a shallower line. You don't, the rank, this is telling us that if you have a certain rank, let's say a high rank, as far as the SAT score, then because this is 0.4, your rank is going to be lower on average with respect to the first-year GPA. But something doesn't make sense here. It's almost like this is suggesting that there's no such thing as data that's like shallow, not steep, that has a really good correlation coefficient, right? So like, yeah, look, this is shallow, not steep. So what, the R is going to be 0.4 because, we go a certain horizontal distance in the X and we don't move that much up in the Y like this shows? Well, no, that's not right. The correlation coefficient has nothing to do with if the data is steep or shallow. This is going to be a high correlation coefficient. It's clustered tightly around the line here, right? What are they talking about here, right? What does this mean? Now, back to the problem of predicting first-year rank from SAT rank. If the two sets of scores are perfectly correlated, first-year rank will be equal to SAT rank. Well, that makes it seem like your performance on the SAT relative to your performance in relation to first-year GPA is based on the correlation coefficient. I mean, that's exactly what they're saying here. It's like if it's a perfect correlation, then your rank won't drop or be affected, because they did talk about how if you had a lower rank in regards to the SAT, then on average you're gonna have a higher rank relative to GPA. But your performance is affected by the correlation coefficient. So it's almost like it's saying that the steepness of the line here, or the steepness of the orientation of the data, relates to the correlation coefficient. But we know that's not true at all. You can have a perfect correlation with a shallow line. If all the data with extremely shallow line, if all the data falls on the line, it's perfect. Or if it's really steep, if all the data falls on the line, it's perfect. All right, so what are we missing here? What's going on? Well, there's two things that are going on here. First, these last paragraphs, this second example we went through in this section, there was two examples. Okay, the second example that's what these last paragraphs are talking about. They're referring to rank. We're comparing ranks, the percentile rank. We're not talking about like explicit scores or like the relation of a score to average. That's what, for all the previous problems, we typically talk about how a score is related to average. But for this example, we're talking about ranks. Okay, and so, but how is that different? That's different because a rank, a percentile rank, is going to correspond to the Z-score. That's exactly what the percentile rank is going to be based on. Well, not just a z-score, but any, because z-score is just for the normal distribution, but even if it's not normally distributed, your percentile rank is going to be based on how many standard deviations you are away from the average. And so that's why even if you have a poor clustering, it's still, if you're just talking about ranks, well, it doesn't matter what the clustering, how well the clustering is. This is going to tell you about the rank. If the R is less than 1, the magnitude, then it's going to drop the rank because as in the Y, because now you're going to be, the more standard deviations you are away from the average, the better your rank's going to be. And again, this isn't just for normally distributed data. However, if the data isn't normally distributed, then you might not have the outline on the scatter diagram be football shaped, be elliptical. And so that's something else that's interesting about this section. For these examples, the textbook has made it a point to state that the scatter plot data, the outline is football shaped, is elliptical. And so we can think about how that's potentially another way you can test for linearity of data. And I'm hesitant to even say linearity, and it's really more you're testing for the applicability of the linear correlation coefficient, right? And so if you have a low linear correlation coefficient like 0.2, well, then it's not very linear, right? Because the correlation coefficient is low. But just because it's not linear doesn't mean it's not really applicable to the linear correlation coefficient. You might have a really low linear correlation coefficient, but it's perfect for it. That's what this is telling you then, and you want to take it seriously. So that's another way of thinking about testing for the applicability of a certain correlation coefficient. You look at the shape of the outline of the scatter plot. Is it elliptical? Is it not elliptical? If it's elliptical, well, even though it might have a low correlation coefficient, but that's fine. Okay, and because this data is outlined with an elliptical football shape, that means we can think of it as linear. That's where this is coming from. The fact that a perfect correlation means that your rank is not going to change comparing the input variable to the output variable is just a characteristic of data that's linearly distributed. So if it was the case that for some data set that on average, if you had a high rank relative to the input variable, you also had a high rank relative to the output variable, well, then that data is not going to be linear. It might be exponential, logarithmic. And this makes sense because when the correlation coefficient is perfect, what happens? Well, the SD line and the regression line are the same because the slope of the SD line is just sigma y over sigma x. You put a minus sign if need be. Well, if r is equal to 1, there you go. And they both go through the point of averages, so the same point, same slope, they're the same. Well, okay, if the regression lines along the SD line, on average, if you move one standard deviation or however many standard deviations away from the average, the point of averages in one direction, you're going to go that same number of standard deviations to get back to the line. Well, standard deviations that's directly related to rank. As long as the distributions are the same type of distribution, whatever it may be, normally distributed whatever, then if you're 1.5 standard deviations above the average, in either case, then you have the same percentile rank. Again, assuming the distributions are the same type. Okay, and so if we think about the idea of a shallow curve with a high correlation coefficient, well, because it's linear, a high linear correlation coefficient, that just means that since r is close to 1, the amount you're moving in sigma x and sigma y to get back to the regression line is going to be similar as far as in terms of the number of standard deviations, which standard deviations directly correspond to rank. So don't let this confuse you too much. We were talking about rank. We were comparing ranks for this last example, not positions of points relative to the average or to other data points within that same column, like we had been doing them with the majority of problems before this. Okay. So now let's work these exercise problems. In a certain class, midterm scores average out to 60 with a standard deviation of 15, as do scores on the final. The correlation between midterm scores and final scores is about 0.5. The scatter diagram is football shaped. Predict the final score for a student whose midterm score is each of these midterm scores. Okay, so we were asked this same question in section 1. But the only difference is now that they're talking about, okay, predict the final score for a specific student. But so what? That doesn't change anything. So we're actually going to get the exact same answers we got in section 1. I'm not going to go through it again. Okay, but now part D is new, but we still could have been asked part D in section 1. This is not unique to talking about a specific individual. But okay, what if the final score for the student is not known? Then what would we predict what if the midterm score we don't know? Then what would we predict the final score would be? Well, our best guess is just the average of all of the final scores, 60. For the first-year students at a certain university, the correlation between SAT scores and first-year GPA was 0.6. The scatter diagram is football-shaped. Interesting way of analyzing it for applicability to the linear correlation coefficient, not necessarily just being linear. Predict the percentile rank on the first-year GPA for a student whose percentile rank on the SAT was, okay, these different percentile ranks. Well, okay, unknown, just 50%. At the average. That's the best we can do. Okay, now these others, let's see. So we need to use the equation for the normal curve. If we've got, so minus infinity to, we need to get the z-scores that correspond to the percentiles they give us for the GPA, or no, for the SAT score. So z, and okay, so 90%. Let's solve this for z. Okay, now let's do this again. 30%. Let's do this again, 50%. Is this right? Why is this so low? This doesn't seem right. So, okay, is this 50, 50? Oh, no, that's right, because it's right at the average. It's zero. This is 0. The z-score is 0. Okay. So, now, the 90th percentile means that the SAT score was 1.28 standard deviations above average. And so, with a correlation coefficient of 0.6, the first-year GPA is going to be 0.77 standard deviations above average. So now let's do that for each of these. And then the last one's just 0. That's why that's going to be 50%, because the regression line goes through the point of averages. So if you were on the average to start with, when it comes to a regression line, then you're going to be on the average. That's going to be your prediction on the average for the output variable. And when it comes to percentile, that means it's the same percentile. Okay, so now what percentile is these standard deviations. So, okay. Minus infinity to this E. Okay. Now, okay. So the 78th and 38th percentile. There we go. Okay. The scatter diagram below shows the scores on the midterm and final in a certain course. 3 lines are drawn across the diagram. People who have the same percentile rank on both tests are plotted along one of these lines. Which one and why? Yeah, the SD line. Which one's the SD line? Yeah, it would be the dashed line. It's like, remember we talked about how with linear data, you're going to have the elliptical shape, and the SD line is going to correspond to like the major axis of the ellipse. And that's what the SD line is. If you're the same standard deviations away, which that's what the SD line is all about, then you have the same percentile rank. So the SD line dashed. One of these lines would be used to predict final scores from midterm score. Which one and why? Okay, so, I mean, the answer is the regression line. But which one is the regression line? Well, okay, we know the regression line is never going to be steeper than the SD line because R is always, the magnitude of R is less than 1. So this is steeper than the SD line, so it's the solid line. The scatter diagram below shows ages of husbands and wives in Tennessee. Why are there no dots in the lower left-hand corner of the diagram? Because, yeah, I mean, people aren't really getting married before age 20. But I'm not sure why there's no data points, so maybe there's some sort of a legal restriction in Tennessee. Why does the diagram show vertical and horizontal stripes? Because ages are going to be reported as discretely. You know, you're probably not going to say 20 and a half years old or 42.3 years old. You're just going to give a round number. Okay, for the men age 18 and over in the Haynes 5 sample, the correlation between height and weight was 0.41. The standard deviation of height was about 3 inches, and the standard deviation of weight was about 42 pounds. The men age 55 to 64 averaged about half an inch shorter than the men age 18 to 24. True or false, and explain, since half an inch is about 0.17 standard deviations of height, then the men age 55 to 64 must have averaged about 3 pounds lighter than the men age 18 to 24. Well, no, false. It's not like you couldn't do some sort of a roundabout analysis like this, where you compared, you have some plot, some scatter plot, and you're kind of like comparing one section of the data to another section of the data. However, that's not what they're doing here. They're comparing. So this is the correlation coefficient that's given, which they used to make this statement here, is, what was it, 0.41. Okay, well, this is the correlation between, let's see, it was the height and weight of men. But this half an inch shorter was based on the ages, men age 55 to 64 versus the men 18 to 24. So the correlation coefficient has nothing to do with age. So no, you can't do this. So false.